All right, here back again at it, recording second lecture of electrochemistry. So I wanted to start by reviewing the learning goals. So for that first video, understand redox reactions, include oxidation states, reduction, reducing agents, oxidizing agents, balancing reactions via the half method. So that's largely review. So if the video that I recorded wasn't enough, make sure that you review that stuff. Okay. Know the basic components of an electrochemical cell, cathode, anode, salt bridge, and be able to write the cell diagram notation. Okay, so we did that as well. And then the last thing we talked about was the difference between a voltaic cell and an electrolytic cell. Okay, so today we're going to do the next three. Why did I even say today? During this video, because it's literally like I recorded that video 10 minutes ago. Anyways, so we're going to do these three learning goals today, and I'll come back and talk about these at the end of this video. Okay, so here we go with section 18.3, standard potentials. So a few definitions, and then we'll talk about what these definitions mean. So the standard reduction potential. So that is the potential voltage of a half reaction in which all reactants and products are in their standard state at 25 degrees Celsius, 298 K. Okay, so key word here is reduction. So this is the potential voltage, or you could really think of this as kind of similar to the energy that's given off for a reduction reaction. The standard cell potential, so there's the symbol, is a measure of how forcefully an electrochemical cell can pump electrons through an external circuit. Okay? And the standard cell potential right here is the standard reduction potential at the cathode minus the standard reduction potential at the anode. So the one place where I think this gets a bit confusing is, so this is a reduction potential minus a reduction potential. Another way you could think of it is a reduction potential plus an oxidation potential. All right? So when I write this equation, E Stell standard equals reduction at the cathode minus reduction at the anode, okay? So this is if they're both as reductions, okay? So I'll say red for reduction, red for reduction. So this is the same thing if I write this as E cathode plus E anode, where now this is a reduction potential, but this is an oxidation potential. So the two potentials, or I can make any reduction potential and oxidation potential, or vice versa, by changing the sign. Okay. So, and I'm going to show you two ways that we can calculate that. So here is a big table of data. So you can see there's a whole bunch of reactions. And the first thing that I want to point out, I've got the equation, reduction half reaction, oxidation half reaction, but this is the standard reduction potential of the oxidation half reaction written as a reduction reaction. I'll give you an example. So if I look here at this fluorine reduction reaction, okay? So it says that it's 2.87 volts, all right, for this reaction to run as a reduction. So if I want to calculate a cell that I make up, let's suppose, so I'm actually going to make this a little bit bigger so I can see everything here. Okay, I'm going to pick silver at 1.99 volts. So let's write that down. That was not the silver reaction I wrote, but let's do it anyways. Let's just go with that silver 2+ reaction. Okay, goes to silver plus, and that's at 1.99 volts. And suppose I want to combine that with something like chloride down here, okay? So Cl2 plus 2 electrons makes 2 Cl minus. And that reduction potential is 1.36 volts. So automatically, if I pick silver, if I pick this to be the cathode, and I pick this to be the anode, and I'll tell you how I know I can pick that one as the cathode and that one as the anode, then I can simply just say E cell is 1.99 volts minus 1.36 volts. And quick math, that gives me 0.63 volts. Okay? So that means if I make an electrochemical cell where this reaction is running as my anode and this reaction is running as my cathode, I'll get 0.63 volts out of that reaction. Okay? Now, if I wanted to, if let's say I'm not so positive about this equation, just doing E cathode minus E anode, and how I know which one is supposed to be which, here's what we want. We want E cell to be greater than 0. We want it to be a positive quantity, and I'm going to explain why by the end of this lecture. Okay? So if I flip this, if I did this the other way around, if I had picked this silver to be the anode and this chloride to be the cathode, I would have gotten negative 0.63 volts, and that would not have worked out. Okay? So you're always going to pick the larger reduction potential as the cathode. So in other words, what you really want at the cathode is the best oxidizing agent. So think about that for a minute, okay? All of these reactions, the way that these are written, all right, and let's specifically talk about fluorine, F2, plus 2 electrons to make 2 fluorides at 2.87 volts. You notice that's at the very, very top of the list. And my list is not complete, like it keeps going down, and it actually would go all the way down into the negative voltages. Lithium is at the bottom of the list. And oh, let's see here. I need to get my book and look this up. It's about negative 3 something volts, and of course I forgot to look that up for you. So okay, that's yep, sorry, lithium solid. Okay, so let me look this up here in the back of the book. It's about negative 3 volts, but I want to make sure that I get the right number written down, because I'm on the internets and people can say, what the heck, dude? Okay, negative 3.05 volts. Okay, so what does all of this mean? Well, if we think about this, since these are written as reduction potentials, okay, what we have here, fluorine and lithium are both being reduced. So that means right here, okay, they're oxidizing agents. And right here, that means they're reducing agents. Okay? So in a reduction reaction, right, these two chemical species, the species that are being reduced, are oxidizing agents. And what this specifically means is fluorine at the top of the list, the largest positive voltage, is the best oxidizing agent. Okay, I'll write that in purple. Best oxidizing agent, and that means lithium plus is the worst oxidizing agent. And as reducing agents, this means fluoride is the worst reducing agent, and lithium solid is the best reducing agent. Okay? So that's not only prevalent in chemistry, how these react in electrochemical cells, but it's also prevalent in what we call the activity series. Okay? When we look at the most reactive species, as it turns out, lithium is way up there in terms of its reactivity as a reducing agent. Fluorine is way up there on its activity as the best oxidizing agent. All right. And so in this list right here, right, fluorine can oxidize silver. Fluorine can also oxidize hydrogen peroxide, but hydrogen peroxide cannot oxidize fluorine. So that's the way that this works, okay? So we can oxidize from the top down, and we can reduce from the bottom up, but not the other way around, okay? So another way we could think of this is, right, noting that once again, we want E cell to be greater than 0. Okay, so if I was just picking a couple random reactions again, let's look at the reaction with, let's say, gold and, actually I want to do something easy. I'll go to, oh, actually, let's see, do I have an example coming up? Yes, okay, I have an example coming up. Let's do that. Okay. Yes, this actually just shows me a calculation. Great. So we're calculating now, this is for copper and zinc. And here you note that both of them are written as reduction potentials, right? Copper plus 2 electrons, zinc plus 2 electron. Copper is positive 0.342 volts, and zinc as a reduction potential is negative 0.76 volts. So right away we see the copper is more positive. That means the copper 2 plus is a better oxidizing agent. But moreover, what that really means is because it has a larger potential, it's positive, that means it's a better cathode, okay? And because the zinc has a voltage that's less than that, it's actually even negative, that means it's a better anode. And so you notice the way that this equation is written here, E cathode minus E anode, 0.342 volts minus negative 0.762 volts makes positive 1.104 volts. Okay? So you got to be careful about that sign change, about the fact that there was a negative potential there. I want to show you another way that we could get to this. All right? So suppose using that equation was a little funky to me because of all that positive and negative sign. All right? So when I recognize that this is 0.432 volts, and I want to balance, oops, people are chatting me up, get out of here. So if I try to balance this with that zinc reaction, then I know I've got to flip that zinc reaction, right? Okay, so I can say zinc solid, and that goes to zinc 2 plus 2 electrons. So now when I flip this reaction, I flip that cell potential, okay? So now, as an oxidation potential, that's now positive 0.762 volts. And I can combine these reactions, electrons cancel, right? And I got zinc solid plus copper 2 plus, makes zinc 2 plus copper solid, and that combines those potentials, positive 1.104 volts, okay? And I arrived at the same answer as if I had used this cathode minus anode, where both species are in their standard reduction potentials. So there's two different ways to do it. As I noted earlier, we can say E cathode minus E anode, where both are as reduction potentials. Or we can say E cathode plus E anode, where this is written as a reduction and this is written as an oxidation. All right? And so again, if we were to make this cell, right, if I were to set up this beaker and the porous bridge and the 2 electrodes and put a voltmeter there, we would measure 1.104 volts, which is kind of cool. Okay, let me get back to one slide here. All right, so here is a good example problem to work on. All right? And let's see here. So let me read it to you, and then I'll play a little bit of music, and we can work through it. So the standard reduction potential of the half reactions in single-use alkaline batteries. is the following. So these two reactions, okay, and notice that they're both written as reductions, right? They're both reduction potentials. What is the net ionic equation for the cell reaction and the value of E cell? Okay, so let's work through that really quick. Okay, folks, so I kind of just worked this problem in two different ways. So I first wrote that perhaps if we couldn't tell which one was the cathode and which one was the anode, then we can get that by balancing the redox reaction, okay? And you still do kind of have to realize that we want to make E cell positive. And also, if you recognize that the cathode has to be the reaction with the larger positive potential, then I kept that reaction that written as is, okay, with the manganese oxide, written as a reduction, positive 0.15 volts. And then I recognized I had to flip the zinc reaction. That's going to make the anode. Another thing I want to point out, you notice that these are called alkaline batteries, and a hydroxide is exchanged between the cathode and anode as well. So that's no coincidence, right? That's why it's called an alkaline battery. I also want to point out, so 1.4 volts, if you go grab a typical alkaline battery, you'll see that it says about 1.4 volts. Sometimes it says 1.5 volts, but that's typical. They're about 1.4 to 1.5 volts. I also want to say that those are incredibly wasteful. I'm going to talk in the next videos about rechargeable batteries, which I've already kind of briefly introduced, right? But voltaic cell versus an electrolytic cell, you got to buy rechargeable batteries. These single-use batteries are so wasteful. It takes way more than the equivalent of 1.4 volts of energy to make one of these things. And then we just chuck them, and they're corrosive, right? They've got this hydroxide in them, okay? So use rechargeable batteries. That's my PSA. I'm probably going to give you several of those on using single-use batteries. Okay. So I think I have another sample problem. Calculate the cell potential of the following reaction. I think you should try to work this out on your own. This is worked out in the lecture notes on Canvas. So you'll have to look up a few different reactions. So you can tell that there's an iron 2 going to an iron 3, and there's a permanganate going to a manganese. So you have to look up those standard potentials. I want you to work through that. I kind of want to move on to the next problem, but I will say that the answer, I'll go ahead and fill the answer in because we need it for the next little bit here, and that way you can check your work. You should get here E cell, pretend I put a little subscript 0 up there. We get 0.74 volts, and it's positive, okay? Positive 0.74 volts is what you should get for this problem. And let me make this a little bit bigger. And I'll show you why we need this for the next one. Okay. So, and again, we want E cell to be positive, and I'm going to shift into why that is now. Okay. So if we look at the definition here of a volt, so this is the units of a volt. Okay. By definition, a volt is a joule divided by a coulomb. Okay. Where a coulomb is a unit of charge. And so if you think about this, so we know that joules are really work, okay, and the coulomb is a metric of charge. So it really is like a work per charge, or a better way to kind of think of that, if we rearrange this, if I solve this equation for work, and again, the negative sign is because it's work done on the system, done by the system on the surroundings, right? This is exothermic work. Our electrochemical cell is doing work for us. So if you rearrange this algebraically, okay, then we could say the work done by an electrochemical cell is negative Q times E cell. Okay, well, what's Q? Q is charge. And that charge is specifically going to be the number of moles of electrons transferred. Okay? Oh, and what I should have said about this previous problem, when you go to solve this previous problem, okay, just like we did above on some of these problems right here, okay, where you see there's 2 electrons in each of these reactions. So that's the number of moles of electrons transferred, 2 moles of electrons. But now what if this was, let's say, 1 and this was 5? Well, I'd have to multiply the top reaction by 5. And that doesn't change the standard cell potential, okay? When I flip these reactions, it changes the sign, but if I multiply this whole reaction by 2, it doesn't make that go up by a factor of 2, okay? So that's where you get this 0.74 volts. I probably should have worked the problem out for you. Geez, here we go. I'm sorry, I'm feeling lazy. So here's from my notes, okay? So basically, here's what happens, right? There's my iron half. Iron 2 goes to iron 3 and makes 1 electrons. And then I have to do this trick, right, where I add like the 8 protons and the 4 waters, etc. But see, when I get 1 electron out of this problem and 5 electrons out of this problem, I multiply this by 5, but it still doesn't change the voltage. Okay? Does not change the voltage. But as we will see, okay, so what I'm going to write here is, I'm going to make this bigger, and I'm going to say N equals 5 mole of electrons, okay? So that's what you would get from this problem when you balance it. So the number of moles of electrons, it does not change the cell potential, but it does change the amount of work that can take place, okay? So for example, now in this equation, if I expand on this, right, and we know that work is negative Q times the cell potential, well then if I plug in that Q is N times F, and there's a negative sign, times E cell, we can see then that the number of moles of electrons does change the amount of work that we do. Okay? So if there was 5 moles of electrons transferred compared to 1 moles, that 5 moles is giving us 5 times more work at the same potential voltage. All right? And then lastly, I want to talk about this F constant. This is a new constant that we haven't introduced yet. This is Faraday's constant. Okay? And so basically Faraday's constant is derived from the fact that 1 electron is 1.609 times 10 to the minus 19 coulomb. So that's the charge of a single electron. It's a really, really tiny number. Okay? But now, if I say, if we do dimensional analysis on this thing, right, and we know if that's coulomb per 1 electron, well, I know that if I say times 6.022 times 10 to the 23 electrons makes 1 mole of electrons, then if I multiply those two numbers together, random stickers and junk flying in front of my board, 1.609 e to the minus 19, or is it 1.602? We'll find out. 6.022 e to the 23, then, oh yeah, it is 1.602. This is what I get for pulling numbers off the top of my head. 1.602 e to the minus 19 times 6.022 e to the 23, and I get 96,485 coulombs per mole of electron, which is exactly Faraday's constant. Okay. So now if we think about the units of this thing, all right, so the unit analysis, N right there, that's mole of electrons. Looks like it says moly. Holy moly. Mole electrons times Faraday's constant, which is coulombs per mole of electrons, times E cell. And we remember here E cell is a joule per coulomb. Then look, moles of electron and moles of electron cancel, and coulomb cancels and coulomb cancels, and we get units of joules, which that's my unit of work. Okay? So now here's an example. Calculate the electrical work done by the following reaction. All right? So this reaction right here, let's see. So this is the same reaction that was right here. And I gave you the results, that it's 0.74 volts and there's 5 moles of electrons transferred. Make sure that you can get to those numbers, okay? And because once we have those numbers, it becomes quite a simple equation, right? It's work done by the electron equals negative NF times E cell. So that's negative 5 times 96,485 times 0.74. I'm doing a really bad example here with units. Let's try that again. Negative 5 moles electrons times 96,485 coulomb per mole electrons times positive 0.74 joules per coulomb. Coulomb, coulomb, moles, moles, all cancels. Then what you get is I get negative 357 kilojoules. So I skipped a step here. So you'll get negative 357,000 joules. Divide by 1,000 and you get to kilojoules. Okay? So that's quite a bit of energy that this thing can do. All right? And so the last little bit, the final piece of information that I want to move on to, okay, is connecting E cell and Gibbs free energy. So remember Gibbs free energy, right? Remember that thing? Okay? For a spontaneous reaction, remember the Gibbs free energy must be negative for a spontaneous reaction. We also talked briefly in our section on thermo that delta G is an alternative name for work. It's the free energy you can use to do work, or really a better way to say that is the energy that is free to be used as work. It's the available energy in the system that can be used as work. Okay? So if work equals delta G, then quite simply, delta G equals negative NF E cell. Okay? And if E cell is greater than 0, then delta G is less than 0, and thus for all positive cell potentials, they will proceed spontaneously. If a cell potential is negative, then delta G will be positive. Delta G will not proceed spontaneously. Okay? And then last, when E cell equals 0, delta G standard has to equal 0, and then the battery is at equilibrium. Okay, great. So I think I have one more example problem after this, and it's another one that's worked out in my notes, so I'd encourage you to follow that on your own. I'm going to sign out of here because I've been in front of my computer recording lectures all day. I'm going to take a break. Folks, I'm going to record I'm going to make a quiz for you for these 2 lectures, and then sometime next week you can expect the second half of these electrochemistry lectures with the second quiz. Okay, hasta luego.